got a nice cover. I think I didn't work quite good. I wanted
Is that covered by the versions of the paper download?
But on the screen you'll see. Yes,
okay.
yes, it's here.
It usually takes them about a week.
It has been, I think, Sabarth noticed it, and I contacted the publishers and told them to make sure they're in.
Yes.
Question where I can stay without shielding the view. Okay, the title was a bit extended, particle model explaining mass and relativity. That is necessary because my mass model depends on a specific interpretation of relativity, and vice versa. Also, relativity depends on mass. And I explain it in a physical way. We have just learned how it can be done in an algebraic way. This is not algebra, this is physics. That is the difference. So why a new mass theory? Because the Higgs theory does not work, as even admitted by mainstream physics. What is the problem with Higgs? The problem is that the necessary Higgs field does not exist, as admitted, and the Higgs theory does not tell us the mass of any specific particle. Why is there an alternative? Yes, there is one. Any extended object has necessarily inertia, and that depends on the finiteness of the speed of light. That is the cause of it. And elementary particles are in fact extended, not point-like, and we will talk about how this can be seen. Why new relativity? A frequent argument which I hear is that relativity of Einstein is the most precise and most successful theory in physics ever, and rethinking relativity is a waste of time. My professor told me this several times. I say no, that's not a waste of time, because it's true. Einstein's relativity provides very correct results, but it's a mathematical construct, and it's hardly based on physics. It has not enough to do with physics. It needs Riemannian geometry, curved four-dimensional space. It's not necessary. I will show it works also with Euclidean space, much simpler. And it does not contribute to open problems like weakness of gravity, dark matter, dark energy, attracting only, and quantum gravity. But that can be solved. So, Einstein's relativity, special relativity, is based on the relativity principle. That means the same physical equations in all frames. And the principle of the constancy of c, speed of light, in all frames. These principles have to be proven to be correct, but I do not see need to take it as principle. We can deduct these rules, these principles, from lower level physical facts, and that is better physics in general. And general relativity of Einstein is based on the equivalence principle. That means, shortly, gravity and acceleration are two words for the same physical process or fact. And the problem is this principle has been falsified. It's not true, and it is not necessary for understanding the phenomena of general relativity. So my talk will follow the sequence. First, talk about special relativity, then about particle physics, which leads to the origin of mass, and then general relativity. Okay, we start with special relativity here. The alternative to Einstein's is the approach of Hendrik Lorentz. And Hendrik Lorentz explained, for instance, contraction as a contraction of fields, not on a contraction of space, which completely, for instance, explains the Michelson-Morley experiment. The important difference is fields are a physical entity. Fields can be measured and are physically understood. Space can never be subject of a measurement. How should that be done? It's not a physical entity, but a mathematical abstraction. The contraction of fields and motion is a physical fact independent of the principles of relativity, was found long time before relativity was a topic. So we have here the pair. What space is for Einstein are fields for Lorentz. This is the history. Heaviside this year, 1888, found that fields had to contract at motion. This was used by Fitzgerald and Lorentz has explained the Michelson-Morley experiment result of Michelson-Morley. By this contraction and these equations, we know that it's a Lorentz transformation follow already from the calculation of Heaviside. Even Einstein has accepted this as an explanation of the Michelson-Morley experiment, but he didn't like it. He called it an ad hoc explanation, and that was really wrong. I think Einstein did not know the calculations of Heaviside, which was a bit typical for Einstein. So, and this relation, that there is a contraction, is true now. It was shown for all kinds of fields, not only for electric fields. So now we have another pair. What time is for Einstein are oscillations in the view of the Lorentzian approach. The important difference is time in the sense of Einstein is again a mathematical abstraction. Oscillations are a physical entity. That means we have to count periods in a periodic process. That is a simple understanding of time, a physical understanding of time. The known oscillations within a particle, this is known, is a physical fact, and this fact is independent of the principles of relativity. And from this follows dilation, independent of principles, very directly, we'll show this. So, this is a general thing. If we have on the lowest level of matter a permanent motion at the speed of light, for instance, you know, Zitterbewegung was mentioned by Schrödinger, then the whole system has dilation. That is unavoidable, and the equation here, this is the Einstein or Dirac light clock, follows from Pythagoras, nothing more, and we can make many examples for it, but this is simple enough. Was often discussed also from Cavalieri in London once and so on. So it's known. We can build a particle model out of it where we also have an internal motion at the speed of light, which is again Zitterbewegung of Schrödinger, which we found for the electron. We have only to extend it to all particles, then we have it what we need. And from this we can build a particle model. That means an elementary particle is built by two subparticles which are massless and orbit each other at the speed of light. And for this model we have some constraints which are known. The frequency found by De Broglie, the speed is speed of light, Schrödinger. It must be orbital because we have a spin and a magnetic moment. There must be two, otherwise the momentum law would be violated and the mass must be zero, otherwise speed of light would not be possible. So this model I call the basic particle model, and say to the beginning it's not in conflict with any electron or other particle experiments. So, dilation. Okay, again I've already mentioned it here. We have our particle with two orbiting subparticles, and now it's moved in an axial direction, and from the circular motion then we get a helical motion, and that is extended. One orbit is longer, and the extension is given again by Pythagoras, and we end up here very simply by the known Lorentz factor. We can also build the derivative of the Lorentz factor, then we know the speed of the proper time of this particle motion. And we can square this equation, then we end up with this. And this has a very good imagination or imaginative meaning. That means if I have a little clock, then the clock has an internal speed, and that is the internal speed of the time in the system. And the clock can, of course, have an external speed. And if I build the vector sum of the internal speed and the external speed, the sum is always the speed of light. Follows very easily from the Lorentz transformation, and I think it was visible here a little bit. Okay, special relativity, to summarize it, is built by contraction and dilation, we have covered it, and the increase of mass. And this increase of mass has to be explained now. To do this, we have to understand what mass is, and this will be our next topic. What is inertial mass, and how is this defined? The basic mechanism of mass is a very fundamental one. Every extended system has inevitably an inertial behavior, even if the constituents do not have any mass at all. That is not an idea or possibility, it is inevitable, it cannot be different. And the cause of it is the finite speed of the light by which the forces within a particle propagate. So, how is this particle built? There are two subparticles which are bound to each other so that they keep a distance. And this can only be done if we have as a binding field a multipole field. That means this particle has a field of this shape, to this side for instance, and of this shape to this side of Einstein. So every particle resides in the potential minimum of the other particle, so this is a stable construct. And this is not new in physics, because we know it. If we bind two atoms to build a molecule, it's the same process of a multipole bind. But here it's not electric, like in the molecule, it's a different force. It's a strong force, you can say in the beginning. So, and this is the equation which describes it. I found this, I could say by trial and error. I've tried to find the simplest equation which describes this. I found this, and it has turned out to work perfectly, so I think it was a good relation. It's easy to understand. Here you have a difference of the part of the distance to the equilibrium distance, and the F is the force, the reordering force, and S is the field of the binding force. So now what happens if we move such a configuration? If we move this particle to the side, the other particle will follow, so that the distance is kept, of course. That's certified by the field. But this cannot function instantaneously, because if I move this away, then it takes some time until the field change of the blue particle goes to the red particle. Until that time, the red particle will stay here, and the field, of course, of the red particle will not be changed. So I need a force to move this particle away, the blue particle away. But after some time, everything is rearranged, the field changes go forth and back, and after some time, the whole thing moves, and I do not need any force at all. And that is the situation that we need an intermediate force to change the motion state of this configuration. And that is what we mean if we say the word inertia. Okay, that's the qualitative thing. Now we can calculate it. Sorry. A bit more. Here, we start again with the equation I've shown here for the force. And now, we imagine we make an acceleration with a constant acceleration, A, and calculate this by using the normal, well-known, this is delay, and this is the equation of school physics for acceleration. All this inserted here ends up with this equation for the force, which I need for an acceleration here. We see at the first, the force is proportional to the acceleration, so we have here derived Newton's law of motion. Newton did not derive it, but we did it here, I think the first time, perhaps. So now we can make some substitutions. We use here, because it's proportional, Newton's definition of mass, and we replace the distance of the subparticles by the radius of the whole system, and end up with this quite simple equation for the mass of a particle. You see it depends on the radius of the particle individually, and of course of the field, which we have now defined. What is the field of it? Here again our mass equation as we have it now. Now to find, we can find the radius of a particle, for instance, of an electron. In a simple way, we know of the electron, about the electron, the magnetic moment. And we use the classical equation for the magnetic moment here, that is it, for a charge E0 orbiting with speed of light. And we combine these both equations to eliminate the radius and come up with this equation. Do you know this equation? I think it's well known. It's a Bohr magneton. You see? And this is interesting because you find in all textbooks that the Bohr magneton can only be derived using quantum mechanics in no other way. But here, I have it done only with classical means. It works. And the next thing we have here, now we know what the field strength is. This is here identical, we can compare it. So we end up with this equation for the field strength. Depends on Planck's constant and speed of light. So, and now we insert this here, and we come to the final equation for the mass of a particle. It's quite simple. Depends on field, on the size of the particle, inversely, and yeah, Planck's constant and speed of light. Okay, that's it. And it's true and works for all fermions. You can use it if you look into the data tables of particles, use the magnetic moment and use the mass, and it works always. And it works also for quarks, for instance. That cannot be done in that easy way, but if you look to quantum mechanics or statements of quantum mechanics people who have thought about this, they affirm that this is also true for quantum mechanical particles like the quarks. So now we come back. This again is a field constant of a strong force. That is something I have to mention. That is not so clear for people following present physics. Okay, the increase of mass, that was our starting point for relativity. It's now very simple because we know at motion the radius, the size, is reduced by the Lorentz factor, so the mass is increased by the Lorentz factor. Very simple. Now, also Einstein's famous equation. If I put an object in motion, the mass increases, and the energy increases by the kinetic energy. If I put this in relation to each other, it's a very simple calculation. We end up with the famous equation. Very much simpler than the way Einstein has done it. And you can do it at school, it's the simpler. Now we can also do another thing. We reorder this equation in this way. Then we have here on the left side the classical definition of angular momentum. And on the right side, we have the Planck constant. That means a constant. That means the angular momentum is constant, independent of the type of the particle. Yeah. Okay, if it's a particle of this kind. Yeah, but that's all leptons, all quarks. Here it's missing the factor of half. But that's understandable because this is not a classical particle in the way that we have half of the mass here and here, but the mass mechanism is different. That causes the missing factor half here. Okay, now the critical point, I say a basic particle model says elementary particles are extended. We have heard also in the preceding talks that assumed that elementary particles are point-like, and it said that this was proven by experiments. But look what the experiments are. What do we do? This is the size of the electron, for instance, is determined by scattering experiments. An electron is scattered, for instance, at a proton, and then the distribution shows a point-like, almost point-like size. But what did we see? We have here the deflection by the electric charge within one of these subparticles of the electron. So the very small size, which is the result, is the size of the electric charge of one of the subparticles of the electron. It's not the size of the electron. It's similar to the Rutherford experiment. Rutherford, wanted to determine by scattering the size of the gold atom. And what he found was not the size of the atom, but the size of the nucleus. Here we do not find the size of the electron, but the size of the charge in a subparticle. This is a different thing. And this is another thing for another story. So now we know if we want to know precisely the magnetic moment of the electron, we know that the Bohr magneton is not precise. We have to do a correction which is the Landé factor. And this correction was historically found by Schwinger in 1948 using vacuum polarization. He has invented vacuum polarization, introduced it to explain this, and was successful, got the Nobel Prize together with Feynman. He called the same phenomenon virtual particles. And the correction, the result of the correction is this value, you see, it's known and a good result. But we also have to do a correction in our particle model. I've made all this derivation of the Bohr magneton only using the strong force in the electron. But the electron has electric charges which change the size of the electron, and that has also to be taken into account. And this can be done, and the result of this correction is this. Look, is there some similarity? It's the same result without vacuum polarization or any other quantum mechanical contribution. Do we need vacuum polarization? For this case, we do not need it. So this is something about virtual particles also. The electron is said to be, by present physics, point-like, but has a magnetic moment and has a spin, and that is very unlogical. So some people from present physics say it's just a point of quantum mechanics, not accessible to the human brain. Others say we have a cloud, for instance, around the electron of virtual charged particles, and they make these effects like magnetic moment, which we need. Okay, could be possible. I don't know whether it's quantitatively working. Or we take this particle model, then we do not need all this stuff. And also we do not need things like renormalization, we do not need any strings which are also invented to come up with those problems. So, another thing about vacuum polarization, we know there is a big discrepancy. Quantum mechanics says vacuum is not empty but filled with virtual particles, and so is energy. Now we can integrate the energy over the whole universe, and we get a discrepancy. We get, as a result, a value for the energy which is 120 orders of magnitude bigger than what we observe in cosmology. That is an unresolved problem, and it's called the vacuum catastrophe. And we have a similar thing to the Higgs mechanism. We have now two models, the Higgs mechanism, and the basic particle model which I've shown you. And what is the problem with Higgs? One problem is the strength of the Higgs field. The Higgs density problem from this theory is this value. This is the vacuum energy needed for the Higgs process. The energy density measured by the cosmological constant and so on is this value. That's very different, and the discrepancy is this 56 orders of magnitude, some people say 60 orders of magnitude, and has also a wrong sign. So, and the other problem is, how is the mass of a particle calculated by the Higgs mechanism? Here, this is the equation from Higgs. There is the parameter V, which is some energy, general parameter, and L is the Yukawa coupling, which is individual for every particle. But the theory does not tell us. If I ask a Higgs representative how I find the Yukawa coupling for the electron, then the answer is always, measure the mass of the electron, and then you can calculate this coupling constant. But that is not what we expect from a theory. The theory tells us before the measurement what the result is. Here, and in contrast, here we have for the basic particle model this equation. If we know the radius, and we can take the radius from the magnetic moment, we can get an accurate result for the mass, which is almost accurate by 1 to a million. Higgs, nothing from this. Okay. This was now particle physics. And now let's start with general relativity. Again, in the Lorentzian way, different from Einstein. What does it mean? First, to Einstein. Okay. Einstein's relativity is logically based on the strong relativity equivalence principle. That is the assumption that gravity and acceleration are two words for the same physical fact and cannot in practice be distinguished for someone in a black box who feels force, doesn't know why. But this equivalence principle is not correct, because both can be distinguished. One case, if the observer has a charged particle object with him, for instance an electron, then this will radiate at acceleration but not at rest in a gravitational field. So if an observer is in such a box, he has to look to his electron. If it radiates, it's acceleration. If it does not, he is in a gravitational field. And dilation occurs in a gravitational field, as we know, but not at acceleration. For instance, at the muon storage ring, that is a very strong demonstration of it. The result would be different. The result of this experiment would be different by more than a factor of 1,000 if acceleration would cause a dilation. So this is wrong. And Einstein's relativity by this way does not have a logical fundament. By Lorentz way, the Lorentzian way does not need it. So a general relativity following the Lorentzian approach can be based on two elements: the variation of speed of light in a gravitational field and the basic particle model which I've introduced. Both is physics, not a mathematical structure. And we only need mathematics at school level, that means Euclidean geometry. In contrast to Einstein, we need the curved spacetime, which is a geometrical model, and so a mathematical construct, and we need Riemannian geometry, and you know that this is extremely difficult. So again, gravity is the change of speed of light in the vicinity of an object, and this is the equation, we know them, which describes the reduction of speed of light in a gravitational field depending on the position. C0 is the undisturbed speed of light. And all phenomena of gravity are caused by this change of the speed of light together with the basic particle model. That is what I would like to demonstrate. We start with the Shapiro experiment. You know, radar ranging between Earth and Venus before 1970, so around. So, can be measured. Now, if we repeat the experiment in the moment when the sun is close to this path, the flight time is delayed, and this delay follows this equation which I've shown, so we can check experimentally that this is the correct equation. We will come to this equation later. It's important that the reduction of speed is directly dependent. For Einstein, it's a different view. Einstein says the speed of light is constant all the way, but the space here is different. Okay, more complicated, I think it is simple. So now we can have this picture. Make us this picture. We build concentric spheres around, for instance, the sun. And on such a surface of such a sphere, the speed of light is constant, but closer to the sun, the speed of light is smaller. So if we have a light beam going through the whole thing here, what happens? It is bended, and this is classical refraction. And to calculate this classical reflection is just a deduction from this equation here, called speed of light. And if we can calculate, for instance, the following things, we can calculate the acceleration of the photon towards the sun at the vertex, and we end up with this equation. And you see, this is Newton's law of gravity, deduced here, not believed as from Newton. And we can calculate the deflection angle, and we end up with, also by reflection, we end up with this famous result of 1.75 arcseconds, which was a great breakthrough, as you know, for Einstein. And from that time on, at that time, Einstein was the only one who has predicted the correct value. But no one at that time has made this calculation with refraction, which not only by the numbers has the same result, but also analytically has the same result like with Einstein. Einstein again says, okay, the path is straight, but the space is curved. It's the other way. I think it's more complicated. So this is now acceleration in the gravitational field in motion, now at rest. Here we have our elementary particles without a gravitational field, the subparticles orbiting. Now we switch off the gravitational field, and this is again a reflection process. We get an increased spiraling down towards the gravitational source. It's like the path around the sun wound up. And the acceleration here again is this equation, Newton, but derived here, produced here. Now, there's another point interesting. The acceleration down is independent on the diameter of this particle, so it's independent on the mass of the particle. And that is the reason why every object, independent of its mass, has the same gravitational acceleration. It's normally called the weak equivalence principle. We do not need it, or we have proven it. It's very clear that it must be this way and not the other. So that was some two examples. Now we have go to general relativity on the whole, and I list here the experimental proofs of general relativity, which you all know, all these, which all prove that Einstein's theory is correct. But if we do it within the Lorentzian way, we also can prove that the Lorentzian way is correct. We have the same results. I've here indicated a little bit in which way this is in detail calculated. I will pick out of it one important thing, that is the Schwarzschild solution, because it's the basis for many of these calculations. You know that these are the Einstein equations for a spherical, symmetrical thing like a star, the sun, or so. It makes it calculation easier. That was the motivation of Schwarzschild. It looks in a popular presentation in this way. And now I will show you how it can be derived using Lorentz. It's not difficult. We start again with this little thing from the Lorentz transformation, and we split it because we need polar coordinates. This is still without a gravitational field. Now we switch on gravity, and we have now taken into account that speed of light is changing depending on direction, And also the extension of fields is changes because this is direction dependent. It's a direct consequence. And we apply these equations to these three terms and end up with this equation. And that's already this partial solution. We can reorder it a little bit and then it looks like this, and this is the form as we have it. Normally this is done with Einstein, and if we do it with Einstein, it looks like this. I've copied this from a popular textbook about general relativity. This is a sequence of more than 80 equations in sequence, but that's not the bad thing. The bad thing is here you have to apply Riemannian geometry, and which is very complicated, as you know, and Einstein field equations. But there are few people who are intelligent enough, perhaps you are intelligent enough to make this calculation, and you have the time, and you make all this work here down, and you end up and get the merit to get the partial solution. Or you do it this way. That can be done at school, it's so simple. And that is not the most benefit, in my opinion. It is simple. The biggest benefit is that if this is based on physics and not on a mathematical structure, concept, or whatever. So now we have seen gravity is the change of speed of light in the vicinity of an object. Now the next question: what is the physical reason for the change of light in the vicinity of an object? And to answer this, I have a little model. Here we have a particle which moves at the speed of light, undisturbed. So now we imagine we have two elementary particles of the type I've shown you here. And here we have the forces which bind these both particles to each other, but they of course act in all directions. And as it is a multipole field, it has attracting and repulsing contributions. And if they interact with this particle, it makes a random zigzag path, which of course is a reduction of the length. So in effect, it's a reduction of the speed. And if we calculate what the reduction of the speed here is, we end up with this equation, which I've shown you several times. It also follows from Einstein theory, but here it's a bit simpler. But of course, I cannot do it now. I have it in my website if you want. So, and another thing is very important. This effect here is independent, this influence, independent of the diameter of these particles. So it's independent of the mass of these particles. That means not the mass of the particles causes this effect, but the existence of the particles. And that means every elementary particle, independent of its mass, has the same influence to the gravitational field, the gravitational effect. Einstein once had said in the beginning, he talked about curved space. And he said curvature of space it happens in the vicinity of matter. He did not say in the vicinity of mass. Okay, later he has taken mass. But in this previous thing, I think it was better. So, and another thing, again, this is strong interaction. So this means gravity is a side effect of strong interaction, and that solves quantum gravity because strong interaction is completely covered by quantum mechanics, so any side effect also must be covered by quantum mechanics, and that includes, yeah, thank you, that includes gravity. Okay? So, open problems in gravity, that's the last part. Here, quantum gravity is already covered, I've just mentioned it. Dark matter and dark energy, that is the discussion we have also here. You know, dark matter is, we have here an imbalance in a rotating galaxy. The forces, centrifugal forces to the outside are stronger than what we calculate to be the gravitational force here. And this is quantitatively described by the rotation curves. You see, this is the radius of the distance of the star to the center of the galaxy, and this is a possible and appropriate tangential or rotational speed. And this is the curve we end up. If we do it with Newton or if we do it with Einstein, it's the same. But what we observe for this galaxy, for instance, are these measurement points. And you see there's a black line fitted to. And there's a discrepancy. The discrepancy is here, this black line here. And this is contributed to dark matter, the halo of dark matter. But if we say, now, as I've done, gravity does not depend from mass, but every elemental particle makes the same contribution to the gravitational field. Then we can take light particles like neutrinos or photons as contributors to the field. And I've calculated this for this galaxy here. And the result of my calculation is this red line. And look how well it fits. Okay, the elevation, how high it is, had to be adapted because I have only limited knowledge about this galaxy. But the shape of the cloud is exactly what we need. So this is really a solution. Mathematically it's a solution, and I think physically it's also a solution. The other particles which are assumed to do this, like axions or neutralinos or so, by all models I know would cause such a shape, and not this shape. This shape can only be done by neutrinos and by photons. So I think maybe a solution. So next thing, the last point in my talk, dark energy. What is about dark energy? First, what is the horizon problem? You know that what is the inflation? You know the horizon problem. That means there are logical connections between distant areas of the universe and which move apart from each other. And the logical problem is that according or in view of the limitation of the speed of light, there cannot be a logical connection. But to explain this, physicists, cosmologists have assumed that in the beginning, short time after Big Bang, space was very small, about 50 orders of magnitude smaller than later. So this distances were so small that even with the limited speed of light, the logical connections were possible. But the problem is conflict between the extension of space and the speed of light, limitation of speed and light. So we have both possibilities to solve it. We can also say we do not think to change the space, but to change the speed of light. So the speed of light was very high in the beginning, went down very rapidly, and now it's slowly further coming down. That's logically completely equivalent. It's a taboo in physics present to say about a change, talk about a change of speed of light, but it's the only reason against this model. I think it's a simpler model and a more physical model, but in conflict perhaps with Einstein. So, and what is the problem with the dark universe? You know, the stars which we observe are on the Hubble line, on a straight line. But what was found now is that here, these are the old stars, are not on the Hubble line, they are a little bit too much to the left, and that gives us, or gives people the conclusion that the younger ones are accelerated compared to the old one. That is the acceleration. You need an acceleration. A cause for the acceleration. One has found the word dark energy. Nobody knows what it is, but it is a word for it. And this is the reason why we talk about dark energy. But if we now make this assumption, speed of light has changed and makes now little changes now, then by the time of these old things, maybe it was this time, speed of light was a little bit higher than now. And the speed of these stars is determined using the Doppler effect. This is this one, you see the speed of light. If we insert here a speed of light which is a little bit greater, then we end up by a speed of these stars which is a little bit greater. They move to the right, as you see, and there's no acceleration any longer and no need for any dark energy. I think this is the solution. Even if you assume that space has changed, also this is can explain it in a similar way. There's no need, there's no acceleration, no need for dark energy. That's my understanding. So, summary. What are the benefits of this particle model? For the mass problem, it gives us a simple working process for inertial mass. It gives us a precise algorithm for the mass of a particle dependent on its size. It gives us a physical explanation for the relativistic increase of mass and for the mass energy equation. The magnetic moment can be determined classically, in contrast to all what you find in textbooks, and also the constancy of spin. And maybe we do not need virtual particles or virtual polarization with all the problems we have with these items. So, for special relativity is founded on physics, on fields and particles, not on geometry. Processes can be visualized, it's easier. And relativistic paradoxes are avoided, you know, the Ehrenfest paradox or the twin paradox, all these things. If you discuss them in the view of Lorentz, there is no problem. It's always a unique solution. Paradox is avoided. General relativity is founded on physics rather than geometry, as here. And easy to understand, there is a very big difference. School mathematics, no Riemannian curve space is necessary. Force number 4, assigned normally to gravity, is not existent. It's not a force, it's a reflection, a side effect, a reflection process, so we are stuck further to unified theory. Anyway, strong and weak interaction is the same. It's not a problem for today. And open problems are solvable like attraction. Only property of gravity, weakness of gravity, dark matter, dark energy, quantum gravity. So, thank you very much. I hope it was not too dense.
Thank you, Professor.
Thank you, Professor.
And Richard has asked me to mount the questions. I just have one question initially.
Yeah.
Do you have another name for it rather than general relativity?
For what?
You have another name to suggest rather than using the name general relativity?
I have used it, I think I call it gravity. It's, relativity.
Theory of gravity.
Yeah.
Well,
But I refer to it because people then know what I mean.
Well,
even though I have a different solution.
that would be consistent with Professor Rowland's remark that general relativity is not a theory of gravity, but a theory about gravity. So we would call yours a theory of gravity.
Yeah.
Okay,
all
that seems very reasonable.
Including all relativistic effects of phenomena of gravity, which we have, yeah.
Yes.
Is this your website, www.ag?
That is the website, yeah.
And this have this PowerPoint presentation on it?
Yeah, I have it on it, and I have many other presentations on it, but I have one introducing to say why a different relativity, then one which has the origin of mass, and one which says the origin of gravity. And these origin of mass and the origin of gravity, I must say I'm proud of it, are the number ones in more than 10 years worldwide. If you go with these keywords into any search engine, you get at the first place these sites.
Okay, my comment is that on the Shapiro effect for the bending of light,
Yes.
the light going by the sun, NASA experiments have shown that when the light is coming at a farther distance from the surface of the sun, so you're beyond the plasma sphere of the sun, there's no bending. But general relativity theory predicts a very measurable amount of bending. So it has been falsified.
There is this Liebach experiment, you know this. It's a very precise experiment. They have proven Einstein's prediction on, with a precision of 5 orders of magnitude. It's very
within the plasma ring.
no, somewhere, but the plasma, if there is a plasma, and the plasma is the reason I know this discussion, the plasma is not so stable. If you have such a precise result, 10 to the minus 6, then this cannot be plasma, because that would be different every day, to say it this way.
Well, but NASA took it at twice the radius of the sun, where it's still very measurable, to 2 or 3 significant figures, and it gets 0.
Okay.
So
that is an interesting information,
and so,
but at least there is no difference between this model and what Einstein has done.
Except
Both,
far out. Except the 2 radii.
yeah, 2 radii.
but that's also in conflict with Einstein, so we are on the same level.
Right, but you're, if Einstein is falsified, are you saying your work is falsified, or are you saying
You say you're doing the same.
In
You're
this,
doing the same.
I'm not so strict fast, but I would say if this is true, then we have to understand why it is this way. That would be an interesting result.
Well, the result is that from plasma physics alone, you predict what Einstein originally predicted, just from the properties of the plasma of on the surface of the sun. And so the people at NASA claim that all that has ever been measured is the effect of the plasma.
I know this, and I had this discussion about plasma from a previous meeting, and I've checked it. Plasma is not stable enough to have such a precise result. This Liebach experiment, this Liebach result, is so precise that it can never be explained by plasma, because every star like the sun has a little bit different plasma. And if this difference is only 1 to 1,000 or so, then this would not work.
But we've never measured on any star but our sun, as far as I know.
What's Liebach?
Maybe
What is a
that-
Liebach experiment, in short?
That was a precise the Liebach experiment, yeah, they have made measurements, I think, maybe with satellites or so. I'm not so sure, but I can give you the source if you want.
Have you ever
I
talked
have
to
it
Dowdy?
at home, but it is a very precise
Have you ever
experiment.
talked to Dowdy?
Hmm?
Dowdy?
At NASA.
Dowdy, I know Dowdy,
Yeah.
but I have the discussion with Dowdy, and I have asked Dowdy to give me a calculation about his plasma calculations. And he always confirms that everything is correct, but he never gave me a numerical result. And so I've said, it doesn't help me to have these statements. I need something written. And then he said, okay, he cannot talk to me, I'm not a partner for him, and so on. Okay, that was useless.
Another question.
Hello. Can I just question a clarification? On your last slide, which you just put up, those are the changes you're making, are they? Just wanted it clarified, that's what the changes you wanted to make?
Which changes?
You wrote out things like,
Well, this is the website. Do you want me to go back to the last
yeah, the
slide?
last slide.
Okay.
Yeah, this is the main website.
I'm sorry, can point to your presentation?
Yeah.
This one?
No, it's
No,
mine.
to the left.
It's one
to the
of them.
left.
One more?
This one. Yeah.
This one here?
Yeah.
Okay,
Yeah.
you wanted to look at the last slide.
Yeah. So go down here.
Yeah.
More?
Yeah. No, that's too much.
Uh-oh.
Before the
Yeah,
end.
to the end. Okay, do it here. I can do it here.
Okay, oh, you're controlling.
51.
Yeah.
The summary. So,
So what did you?
so those are the changes you're proposing, is it?
This is his results.
Well, these are
For
not,
special
these are
relativity.
results. I think these are the results of the.
For,
model.
for special relativity is founded on physics and not on geometry. Is that your change you want to make?
What I've shown here, the Lorentzian version, what I call the Lorentzian version.
So you want it
It's not
Lorentzian?
Simon geometry.
Yeah.
Lorentz did not want to do it with geometry. Lorentz, in the case of the Michael-Morley experiment, has
Yeah.
done it with fields. And he has referred to Heaviside, to Oliver Heaviside, who has made this calculation about fields.
Yeah.
And this is a change, what I've shown you.
You want to change
This is
to?
a change.
You want special
And
relativity?
Further change,
describe
I
what
think,
he
is
has
necessary.
done.
You're saying that
What he claims he has done,
Yeah.
not what he wants to do.
The same general relativity can explain by a field theory.
Okay.
By the fact that, indirect, but more precise, by the fact that the speed of light is dependent on the position. And this model, of course. This
Well,
both
the speed of
together.
light is dependent upon the potential. As the potential changes, the speed of light will change.
I've shown you the process of disturbing the path of a light-like particle in the vicinity of an elementary particle. That is the cause, and I've calculated it numerically, it works. Yeah? Whereas in this equation, and okay, I'm not sure that I should show it now. No, in this equation I do not have the mass because it doesn't has this influence according to this model, but instead of m I have n, and n says the number of elementary particles. So the gravitational field of the Earth, it does not depend on the Earth, on the mass of the Earth, but on the number of elementary particles which we have in the Earth. It's not a great difference in practice. Huh? But for these things it's different.
That's all we have time for. You have to continue discussion at the coffee break. Thank you again, Albrecht.
Richard, I wanted to ask everybody who's driving a car, can you raise your hand?